Lesson 1.1.1, periodic motion. There were two equations that we worked with here in this section, the first of which was Hooke's law. Hooke's law states that the force exerted on a spring is equal to a negative sign times our spring constant times our displacement, which is x. So this is force. This is our spring constant. This is our displacement. Displacement is how far it's stretched. The other equation we looked at was the potential energy in a spring. And our potential energy in a spring, so we have PE for potential energy of our spring is equal to 1/2 our spring constant times our displacement squared. This square is going to be a critical part of our calculation a bit later on. Let's take a look at practice problem number 1. In this practice problem, it says, what is the spring constants of a spring that stretches 12 centimeters when an object weighing 24 newtons is hung from it? So let's summarize our given values. The first thing we're given is the displacement. The displacement is given as 12 centimeters. Now what we'll notice is that 12 centimeters doesn't jive with the spring constant we're familiar with. That requires meters. So if we want to convert this into meters from centimeters, 1 meter is 100 centimeters. We have our displacement in meters. The next value we're given is the force. Our force is equal to 24 newtons. But because this force is pulling down on the mass, we indicate that this is a downward force with a negative sign. A positive force would be going upwards, and negative force is going downwards. They express this orientation in example problem number 1 on page 385. So give that one a look. See if you can find where the force downwards by the sack of potato is 56 newtons, but they express it as negative 56 newtons to show that it is in the downward direction. So the negative symbol represents. And finally, the value we're looking for is K. The equation that we're going to use is Hooke's law. Hooke's law involves F equals negative Kx. If we're solving for K, we're going to need to make a few small changes to this equation. Let's make those changes now. We're going to multiply both sides by -1. Our goal is to isolate our unknown. This is the unknown that we're trying to isolate. Our next step in the procedure, we'll multiply both sides of our equation by 1 over x. When we multiply both sides of our equation by 1 over x, we have negative f over x is equal to k. We can sub in these values. Our negative f is negative 24 newtons over x, which is 0.12 meters. That's equal to our value of k, which equals 200 Newton over meters. We might also express this as 2.0 times 10 to the 2 Newton over meters. Therefore, the spring constant is 2.0 times 10 to the 2 newtons over meters. If you have a word question, we should probably have a word answer. What is the spring constant of a spring that stretches 12 centimeters when an object weighing 24 newtons is hung from it? The spring constant is 2.0 times 10 to the 2 Newton over meters. Let's do another example here. Let's look at number 4. In question number 4, we're given that a spring has a spring constant of 256 Newton meters. So what am I being given here? Well, I'm being given my spring constant. A spring has a spring constant of 256 Newton over meters. How far must it be stretched? Well, that's displacement, and that's my unknown. So how far must it be stretched to give it an elastic potential energy? So that's that PE value of 48 joules. Which equation are we going to use? Well, there's only one equation that includes potential energy, and that's the potential energy in a spring equation. Now we're trying to isolate x. To isolate x, we're going to have to eliminate all of the other variables on this side of the equation to get x all on its own. Let's start by multiplying both sides by 2. All right, we're almost done. We've isolated x, but it's got this math function, this exponent around it. To eliminate this exponent, we're going to need to take the square root of both sides of our equation. The square root of x squared is equal to x. Now that we've isolated our unknown, we can plug and solve. So let's plug and solve. 0.61237. Now, we had 2 sig figs and 3 sig figs. We need to round this answer to 2 sig figs. There, we've got our displacement. Let's look at the review question number 12. In the review question number 12, it says, how must the length of a pendulum be changed to double its period? How must the length be changed to halve the period? Well, first off, we need the period of a pendulum equation. So one thing that we might notice is that the period and the length are directly proportional. This means that when the length increases, the period increases. When the length decreases, the period decreases, because the period is equal to a whole series of values, including length. When the length goes up, because it's on the numerator, the period will also go up. But t isn't directly proportional to just the length. T is proportional to the square root of length. So what does this mean? Well, this means that if we were to double the period, ignoring all the other terms, what value would we have to put in this position in order for us to double the period? The answer is 4, because the square root of 4 is equal to, you guessed it, 2. So because period is directly proportional to the square root of the length, in order to double the period, we would have to increase the length by a factor of 4. To halve the period, we would have to decrease the length by a factor of 4.
If we're going to work with this algebra, we need to make sure that we're developing our algebra skills. If you're struggling with this right now, that's okay. But for these struggles to not continue, we've got to learn some algebra. So stay in touch. Give me a shout. Contact me if you need any help. We'll work through this together. Good luck. Talk to you guys again soon.